Okay, so this is the pre-calculus review for chapters 1 through 5, and in this video I will discuss numbers 6 through 10. Okay, so number 6 gives us two functions, f of x and then also g of x, and it asks us to calculate the composition and then find the domain of that composition. Okay, so it says, what is f of g, which can be rewritten as f of g of x. All right, so we want to go to the function f, and we want to replace the input x with our input, which is g of x, the entire function g of x. So what we can do is we can say f of g of x. We can rewrite our function f, and in place of x, the input, we're going to put the input, which is function, which is g, 3 over x minus 1. So 3 over x minus 1 is going to be the input for the function f. All right, so now if we simplify this algebraically, what we can do is we can multiply 3 times 3, and we get 9 over x minus 1 minus 1. Not a whole lot we can do algebraically there. Depending on how the answer is written on the EOC, I want you to be able to find a common denominator. And what we can do is we can rewrite 1 as x minus 1 divided by x minus 1. And the reason we're doing that is because the denominator for the left term is x minus 1. So what that looks like, 9 over x minus 1 minus x minus 1 over x minus 1. So now that our denominators match, now we can combine the numerators here. So we can say 9 minus x minus 1 all divided by x minus 1. Let us simplify this. We can distribute the negative. So we get 9 minus x plus 1 divided by x minus 1. In the final simplification there, we can combine like terms, negative x plus 10 divided by x minus 1. So here's our final composition, and depending on how it's written, they might say that the original guy is our final composition. So there's a composition. Now it asks us to find the domain. So to find the domain, we have to consider two things. We have to consider the domain of the composition, the result. So the domain of the result. We also have to consider the domain of the input, which was g. So we have to be concerned with those two things. Again, in this situation, just like the other problem, problem number 1, it looks like those two domains are going to be the same. Okay, so let's look at the negative x plus 10 divided by x minus 1. And let's look at the domain of that. So negative x plus 10 divided by x minus 1. What we want to do is we want to look for any red flags. One of the red flags we see here, or the only red flag we see here, is division. And remember, we can't divide by 0. So we know that x cannot, or x minus 1, the denominator, cannot be 0. So we can actually write that out. We can say x minus 1 cannot be 0. If we solve that, we simply get that x cannot be 1. And in fact, that's the domain here. X cannot be 1. X can be anything except 1. Notice that that's the only thing we can plug into the function that's going to make us divide by 0. So then if we consider the input function, which was g, g has the same denominator as our result. Therefore, the domain will be the same. So the final answer for the composition, negative x plus 10 divided by x minus 1, and the domain is x cannot be 1. Okay, number 7. Number 7 is a dreaded word problem. A dreaded word problem, it says the marginal cost given by the variable c in dollars to produce x portable 12-inch TVs is given by this function. So they're actually kind of doing all the hard work for us. They're actually giving us this function. Okay, so they're telling us that the cost to produce the number of X TVs is given by this function. So an important word there, the cost. So typically we want to minimize costs. And so the problem says how many TVs should be produced to minimize the marginal cost. Now, if you look at the function here that we're dealing with, this function is a quadratic. Now, we know the shapes of quadratics. We know they are parabolas. This particular parabola, since the leading coefficient is positive, since it's a positive 1, we know that this parabola opens up. We're really not concerned with the exact location of that parabola, but we do know that it opens up. And any parabola that opens up is going to have a minimum. And also, it doesn't apply in this case, but any parabola that opens down is going to have a maximum. And that maximum or minimum is going to occur at the vertex of the parabola. So this guy right here is the vertex of the parabola. Again, we're not concerned with the exact location. We just want the general shape so we can understand the problem. Okay, so basically what we want to know is we want to know how many TVs should we produce to minimize the cost. So we are looking for this point. We want to know what is that point. And the X value at that point is the number of TVs that we should produce. Okay, so to find that point, we know it's at the vertex. We can use the vertex formula. And the vertex formula says that the X value of the vertex has to happen at negative B over 2A. B in this situation is negative 80. And A in this situation is a positive 1. Okay, so if we simplify this, we have a negative 80 divided by 2 times A, which is 1. If we simplify this, this is 80 divided by 2, and 80 divided by 2 is 40. So what that means is we know that the X value of the vertex has to be 40. So then the last part of this says, what is the actual marginal cost? So to find the actual marginal cost, all we have to do is plug this X value in to the function. So we're going to take 40, and we're going to plug it in for X into this function. Okay, so C of 40. So the marginal cost for 40 TVs is 40 squared minus 80 times 40 plus 2,000. 40 squared is 1,600. 80 times 40 is 3,200 plus 2,000. So if we do that math, let's see, we get 1,600 minus 3,200 is negative 1,600 plus 2,000 is 400. So the marginal cost at 40 TVs is $400. Okay, so the important part to that one was recognizing the shape of that graph, understanding that the minimum had to occur at the vertex, knowing the vertex formula, and anytime you have a parabola, the minimum or maximum has to occur at the vertex. Okay, number 8. Number 8 is asking for several things, but the function that we're dealing with is a 4th degree polynomial, and the degree of the polynomial is important, and you will see how that comes to play here in just a moment. So as I'm looking at this function, the first thing going through my head is I see x's in everything. In fact, I see 2 x's in everything. So I'm immediately thinking that if I need to, I can factor out an x squared. In fact, let's go ahead and do that. X squared, if we factor that out, we're left with x squared minus 2x minus 8. Okay, so then the first question says, what are the maximum number of x-intercepts? So the maximum number of x-intercepts is always equal to the degree of the polynomial. And in this situation, the degree of our polynomial is 4, so the maximum number of x-intercepts has to be 4. Okay, for part B, B says find the actual x and y intercepts. Okay, so to find the y-intercepts, that's the easy part. All we have to do is plug in 0 for x. So to find the y-intercept, plug in 0 for x. So if we do that, guess what we get? We get 0 minus 0 minus 0. And in that situation, that's going to be 0. So the y-intercept is 0. So the y-intercept is actually the point 0, 0. Okay, the x-intercept, slightly more complicated. To find the x-intercept, we have to set the entire function equal to 0. And so that's why factoring kind of helps us out, because then we can use the zero product property. Okay, so x squared times x squared minus 2x minus 8 equals 0. Easy part here is x squared equals 0. That's a double root. So we have two things here, x equals 0 and x equals 0. So that's one of our x-intercepts, is x equals 0. Okay, now the other factor is quadratic. X squared minus 2x minus 8 equals 0. To solve this thing, the first thing we should check for is look to see if that is factorable. If it is factorable, we should factor it, then set each factor equal to 0. And it looks like this one is factorable. It looks like we can factor this as x minus 4 times x plus 2. And now we have the product of two things equals 0, so we can set each one of those factors equal to 0. So x minus 4 equals 0, and then also x plus 2 equals 0. When we do that, we get x equals 4, and we also get x equals negative 2. So there are all four of our roots. X equals negative 4, x equals negative 2, x equals positive 4, and then x equals 0 twice. Okay, so the fact that x equals 0 twice is important to us, because part C says, does the graph touch or cross the x-axis at each one of those x-intercepts? So remember, if the root occurs an even number of times, then the graph just touches the axis at that point. So in the case of 0, for x equals 0, because it happens twice, which is an even number, the graph is just going to touch the axis there. At x equals 4 and x equals negative 2, because that only occurs once, which is an odd number, it's actually going to cross through the axis at those points. Whoops, that's a positive 4 and a negative 2. It's actually going to cross the axis. Let's look at the graph of that, and you'll see exactly what I'm talking about. Let's see here. Let's graph this original function. Y equals, f of x equals x to the 4th minus 2x to the 3rd minus 8x squared. Let's graph that thing. And we should see that at 0, the graph actually bounces off the axis. At negative 2, the graph actually crosses through. And then at 4, it actually crosses through as well. So let me throw that picture up here real quick so you can see exactly. There it is. So you can see that at 0, it bounces off the axis. At negative 2 and then also 4, it actually goes through the axis. Okay, so that was number 8. We had several parts to that. I had to know a lot of stuff to do that problem. Okay, number 9. Number 9 asks us to find two things. It's giving us a rational function, and it asks us to find the vertical and the horizontal or oblique asymptotes. So remember, to determine the vertical asymptote, all we have to do is we have to set the denominator equal to 0. But before we do that, let's look to see if either the numerator or denominator is factorable. Looking at the numerator, it looks to me like it is not factorable. I can't think of any numbers that multiply to be 3 that add to be -1. So I don't think that's going to factor, so we're safe. To find the vertical asymptote, all we need to do is set the denominator equal to 0. So x minus 2 equals 0, so then x equals 2 is the vertical asymptote. Okay, so now to determine if there is a horizontal or oblique asymptote, we have to look at the powers and the terms of the leading terms. So the terms with the highest powers. So the numerator has a power of 2, and the denominator has a power of 1. So that means that the numerator is larger. Because the numerator is larger by exactly 1, that means that we have an oblique asymptote. To find the oblique asymptote, we need to just divide exactly like it looks. So we need to divide x minus 2 into the numerator, x squared minus x plus 3. Okay, so to do that, we should use synthetic division. We should use synthetic division because the denominator is a linear term, meaning it's a line, x plus or minus something. So what we can do is we can say that our reference number is 2, and we can figure that out by setting x minus 2 equal to 0. And then write the leading coefficients, or I'm sorry, not the leading coefficients, the coefficients of each term to the right. And then we're going to bring down the first term, which is 1. 1 times 2 is 2. Add up these two terms, and you get 1. 1 times 2 is 2. Add up those two terms, and we get 5. Now, 5 is really irrelevant to us because 5 is just the remainder, and it doesn't mean anything when we're trying to find the oblique asymptote. We talked about why that was in class, but I'm not going to go into that here. So all we have to do is look at these terms, at those numbers, and we are going to make those the coefficients of our oblique asymptote. And so what happens is this becomes 1x plus 1, which is just x plus 1. So our oblique asymptote is just x plus 1. Okay, if the two powers in the numerator and the denominator were equal, then all we would have to do is divide the leading coefficients. And if the denominator's power is larger, then the horizontal asymptote would be 0. Okay, last problem on this video, number 10. Number 10 is, again, a rational function. And all it's asking us to do is find the domain. Now, this one should be pretty easy because all we've got to look for is any of our red flags. And we know that our red flags are taking the square root of a negative number, taking the log of a negative number, and dividing by 0. The only thing we have here is division. So all we're concerned with is dividing by 0. So we want to make sure that our denominator, x minus 7, never equals 0. So when we solve this, we just know that x cannot be 7. That's also where your vertical asymptote would occur at x equals 7. So for the domain, x can be anything except 7. That's it for this video. We will do the next problems in future videos.